looking at the third and final here session I have on secrets management for critical infrastructure. And it really picks up where we left off with ecosystem to talk about the provisioning secrets, the providence, device provisioning, and kind of that whole ecosystem of the 4 trust accountability chains, but how actually the implementation of it is done, not logically, but how we would implement this in the devices and what design components need to be thought about and included, because at this point they just don't exist. But we're still, I keep bringing this up because we're answering these 2 questions that everybody's seen. And in this training, I'm mostly going to focus on this product lifecycle trust accountability chain. So we're going to start out by talking about a minimum set of security components that would have to be distributed in each device. So it'd be kind of like a TCP/IP stack is distributed on each device on the network, so we know exactly how to communicate to the network. A base DNA in every device for the minimum set of security components would have to be implemented in each device. Now that, when I'm talking about programming that, I'm talking about that putting into hardware as it's brought up and designed in. But to retrofit, that's a software block that's programmed in. Dangerous, not, as far as extraction, but possible, yes. So I said now, I don't know if anybody's familiar with a project by Tailored Trustworthiness Space. It was a DoD project where they looked at what's required for each device, and on a network, on an embedded system network, on a SCADA network, whatever. I think they were mostly looking at SCADA. There's a device and then a downstream devices, and the device would have some management, and some devices would be agent devices, and then they would have services, but all of them would have a set of policies. And I really I like this work, except for that I would add one thing that, as we've learned in manufacturing in the modern age, modularity is really key. If we could make the same components, minimum security components that go in everywhere, and we might not implement them in where they're not required, but at least kind of map them out like your TCP/IP stack. This is the minimum set of things that has to be on every device to make them all play and work in the security ecosystem. And that's kind of what I just said here is, what is that minimum root secrets, and what is required to restrict access to them, and what functionalities are required, security functionalities at this base operation. Because the TCP/IP stack has the network layer, which is physical, but then it has how you're allowed to interact with the physical in some of the higher levels, and then how you interact with the applications at the highest level. So those have to be defined. So that for security, they have to be enforced so that you can only access these root pieces of the security feature in every device by the accepted manner. So if you look at now, if I were to make what contents would that root DNA have, and kind of separate it by where they're needed and what you need for each level in the providence. And you see I have in manufacturing, you need to start out with a way to program it and have a transport designed into it so that it can be uniquely programmed and even securely programmed. And then what you would be doing with that program and transport is in kind of the next level. I call it supply, but it's in that manufacturing supply step, and it's programming in vendor information. And that's the next kind of block down: unique device information, vendor certificates, vendor information, configuration, so the device is hard configuration so that you can use the configuration on startup and self-check. And then the next level, you'd say, after the device, it's got to be programmed and put on a network. So you have to have a way to, using the vendor pieces that you already programmed, build the next level of trust in the chain using that. So the vendor then, the network programming things would be done using the vendor provision pieces. And likewise, once it's on the network, the active management and operation adds another piece based on the network components that it can use during operation and roll and rotate and change out to refresh the security posture. So then all the way on the right is now what becomes the whole piece that's required in that center piece, that center DNA of every device. And this isn't an official formative end-all be-all, but this is a good place to start as to what types of things need to be in there. And a lot of this is not just what things are in there, but then how they're allowed to be accessed. Because you don't want anybody just to be able to ask the security DNA, the security root for a cryptographic key. It has to be done in a certain way. A big piece of this then becomes if the vendor information gets programmed and at the network level, that bottom blue block, or say at the network level, or the installation level, this network information becomes compromised in operation. Now you can fall back in the chain to the information that was programmed in the supply to reprogram the network piece. So cascading becomes important as to how do we maintain the trust chain and be able to recover security posture. So the operational piece is continuous renewing from the network piece. But if the network piece ever was compromised, one, you have reprovisioning of the network piece, and you'll see I have a network exchange key, would allow you to renew some of the network stuff on a recurring basis, and certificates and whatnot. You use a certificate authority to do this piece. But then the operational is done whenever the sensitivity of that network requires rekeying, retooling, and changing security posture. But then if you had a total failure and compromise at that network level, you could always call in your vendor representative, probably an industry that doesn't exist, a reprogramming and secrets management industry. But accountability of this at each stage is maintained with, like the vendor maintains accountability. So if all of a certain type of vendor products get compromised, you know where they're all at. You can then have accountability of that vendor. And when you start holding companies accountable for things, past actions, their actions change, let's put it that way. And then a lot of the feature of their security is logistics based. Instead of just throwing products over the wall, you use them how you see fit. They need to support that later. So here's a more defined, I mean, I've taken a lot of time in a lot of different customers that I've worked with, implement different pieces of this to really identify what this would kind of look like. And the different installed at different places. I had an article I published about a month ago on the need for asymmetric and symmetric in critical infrastructure. And it basically comes down to it that because of the differences we talked about in the first session, that there's a divide between the needs for having people in the loop in IT and the needs for kind of synchronous operation. You need to have both capabilities, and at different times need both. And that's a big feature of how do you bridge that gap, is to really have both. And not say IT says you just implement our security, go run with it, and industrial control says no, we do it this way, you change it. It really needs to, both sides of this need to come together. So being able to fall back to the build trust, establish providing all cryptographic operations from this single kind of cryptographic key management block, and defining the algorithmic implementation and not specific cryptographic algorithms. Algorithmic implementation, I mean asymmetric, symmetric. Don't say that this has to be this length of key and this whatever. make the capability to grow and migrate should this need happen, and identify what types of operations instead of what length of key and what algorithm. But things that would be standardized, vendor requirements, interoperability between vendors and network providers, product lifecycle, that's kind of the provenance piece, third-party trusted operations, how do you set up trust between every handoff and handshake, and then data retention and management, how much data and what is needed to be retained every time you make a transaction and pass it on to the next level, so you're not just throwing them over the wall, like I said, and they take it. You have to say, I stamped that I did this and I turned it over to you and we had a handshake and I have your cryptographic transaction of receiving it and you have mine of signing off on it, and we maintain those. So the logistics part now becomes part of the security posture. So what does this look like on kind of the top one? Just look at the top piece there, supply chain. A unique device ID, provisioning transport. These are interesting because, see if I put it up there. What you have when you're programming these devices, you're hooking up to an industrial control system and you're rapidly programming multiple devices in factories. So renewal of that transport is part of the provisioning process, and some implementations I worked with, they would actually prime the provisioning transport every time they used it. So they'd roll it with a number only known to them. So as part of the programming, you can't reprogram it without destroying what was already programmed. So setting up the first step in the chain requires that type of detail to make sure that you as a manufacturer or them at that level are keeping control over that programming process, not letting anybody else do it later on down the road. And then secrets of boot verification connect really close to the configuration. So you take the base memory block, you hash it with the boot secret, and you produce a signature, and that signature then goes along with the firmware. Won't operate unless it has a signature. And this all has to be thought about and designed into the design stage of the devices, including supersession. So how is your keys transferred and turned over? If you just send it something new, somebody can use it's almost like a denial of service attack where they've done on devices that allow people to change keys, and they trigger, people have learned to trigger the key change without having a new key, and there's no way to fall back, and it prevents a denial of service. I've actually seen that one done on a product basis with a company where somebody just found out how over the internet to basically lose all the keys for a certain product, and it just kind of bricked it, and people threw it away, and nobody bought that product ever again, and really damaged the company's reputation. But vendor certificates, what at the vendor level needs to be kept and turned over in one product, so that now if you have multiple vendors on your end user network, you can look at the vendor certificate and find out where it came from and information about it that's important over the life of the product. As well as some asymmetric keys for using at the vendor level. So can the vendor then send something to it from them that's kind of blocked? Do they have the ability to send something down for patch management and things like that? And then proof that they actually did that. You have a question?
With our conversation before, we were talking about the auto manufacturer and having to reflash something and somebody to put it down.
Mm-hmm.
So you need a public key so you can make that recognition that you're the correct person to reflash. Mm-hmm.
Yeah, there's several reasons that would be used, both a signing and encrypting, so that this device can encrypt something outgoing and can sign something based on its configuration that's provably from this device. But all this has to be thought about in that initial stage, and then whenever network is programmed, certain aspects of this have to actually be not trumped over but hidden. So when superseded, so when a network vendor programs something in, what pieces of it need to be covered up from the vendor, so that now you use that particular cryptographic operation from the network and not the vendor. But yet you can go back if you ever compromise entirely at the network level. And once again, asymmetric sessions supersede for the vendor and symmetric for deriving. So a big thing we have in embedded system networks and critical infrastructure is the need for continuous operations and availability. So the need for disconnected operations becomes important. How can you set up that without losing your symmetric or your synchronous operations? Anybody familiar with how a garage door opener works? Whenever you click the button, it communicated with it and synced with it last time. You click the button, it says the operation usually, and it says roll to the next key on both ends. So both ends now roll from one key to the next, and it's just a big long key, and they mathematically put in an increment number sometimes, just 1, 2, 3, 4. So if you've hit the button 1,000 times over the life, you're on the 1,000th roll of the new key. Now both ends are doing the same thing, and they both can do this at 2 different points and multiple points, and they can come up with the same number, but there's no way you could calculate what that number is after 10 years. So that type of technology added in brings your symmetric and asymmetric capabilities together, which is what's needed in this, the IT side and the industrial control side. And the security posture renewal, because you can always resend back to the lowest level if you need to go back to the vendor programming, or change out segments of your networks. If something's compromised and you think it's this segment, let's change everything on this segment. Let's rekey, let's retool. In general, there's a lot of ways to think about this, but it's a symmetric and an asymmetric method of key exchange and renewing security posture rapidly or human triggered. And then in the operational, we kind of come to really a lot of the same needs. How do you roll? How do you renew your posture? How do you maybe hide some aspects of the network provisioning with the latest one? And then on top of that, if you have a roving network, now I can have multiple network blocks and multiple operational blocks. So everywhere I've put in my PEV, it just adds another block of network for that network. And what you can do is you can double sign a home network block and have accountability for billing remotely from one place to another, and bill it back to the home location. Provably, cryptographically prove a roving device where it is anywhere in the network, anywhere in different networks, as long as those networks can connect through a CA, Certificate Authority. Any questions on that one? People familiar with a CA? I figured. Go ahead.
Think of a control system, different control systems, and let's say in a chemical plant, you have part of the control system that says you pour 10 gallons of X into Y, and there's a command for that. That, in my mind, or that may or may not need a secret or need a cryptographic capability attached to that. Whereas if maybe we're having a SCADA system and you have something that is done remotely and there's a communication link that maybe uses TCP/IP or whatever outside, then you say, it sounds like that might be useful to have some kind of confidentiality or that kind of thing. Can you maybe drill down, and maybe this is the right place for that, where in the control systems process where you would have use cryptography, and maybe where it might be a good idea, but the memory and the control systems, and because controller systems are really dumb and they can't really, because I understand if you use cryptography in certain parts of a control process, you can shut down the whole plant. So how we think about the use of cryptography in billing and on that, the human resource side and the accounting and the business side, that's good. but not necessarily, do we use it in the control, in the controls that are actually running the plant? So they're,
And absolutely, that's why you see that I'm showing keying for symmetric and asymmetric. Anywhere that a human-based operation, something that's queued, you use asymmetric cryptography because that's what is used in the IT world. But if you have rapid communications, it's done all the time. These systems can use symmetric cryptography to communicate and be within those defined time requirements. They can actually use these two different processes in both instances. And that's really why both are needed at every stage, is because you have certain operations that have to be done that require queuing and that asynchronous actions. But then you have the need for command verification across and trust across the network to be set up with synchronous and symmetric cryptography. And that's done as well. So as far as looking at the security root on both of these that's going to be on every device, you have to have kind of both capabilities. Does that make sense? So you use one for human, anything that goes up to the enterprise network, but you can still use the other type of cryptography
inside the control.
And that actually helps with the trust of that network over multiple hops. Make sense?
I understand it. One has to then drill down to what kinds of algorithms you can use at what point that's enough.
And that's why I just separated into symmetric and asymmetric, because the whole which algorithm to use, NIST has volumes on that. And I think I would look at that and say, whatever if I'm designing this control system, and it's got to be replaceable and replenishable, and that's why I said the biggest thing with security postures, you have to be able to reset it and renew it, because nothing is going to last forever. So plan for that and design it to recover, and that's what we're talking about here. And the same with restricted use. There's going to be a kind of a hierarchy of what times and what components are allowed to have access to what, even within the device, and for communication and for whatever. This might actually point out some of what we were talking about. But as far as symmetric provisioning of vendor unique IDs, they're hooking up to a ICS machine, rapid programming. They need symmetric. Especially when you're programming in a non-trusted environment. So I've seen these set up where you had customers programming in the Philippines and they couldn't send your secret. Nobody over there was allowed to have access to what was being programmed in the machine. So you use that programming transport and uniquely masked every devices with a random and sent over the random and the mask and programmed each device uniquely. And the subcon has millions of random looking numbers that mean nothing to what's in the device. And the programming was done with a high security module on site. So those operations are valid now for distributed manufacturing and control over those environments.
Didn't it be signed other than DES?
What's that?
Other than DES for symmetric?
Yeah, AES, DES, help me out. Cryptographic algorithms for, what's that? ECC. ECC is asymmetric.
Yeah, I'm sorry. You're looking for symmetric?
Symmetric, right?
Yeah, well, I'm just, we have different examples. So DES is a traditional,
DES is a symmetric, AES.
But AES is so much powerful, so I didn't know, and this is for another course, because using AES somewhere in the control system might take it down. I think it's too much, but
AES is predictable time for operation. You can determine, it's deterministic, you know how long it's going to take to implement each transaction.
I was thinking as an advanced DES, sorry.
Okay. DES is the same. DES and AES are kind of the same way. With that symmetric algorithms, you can predict how long it's going to take. So they fit well into deterministic communications for machine operations. Asymmetric operations, give me some asymmetric, electric, ECC, RSA, key length, every key, every time you run an operation, it takes a different amount of time. And it's seconds sometimes, depending on how powerful the machine is. It's a big differences, and it's not predictable. So that is masked well by human operations, which is why they've mostly implemented IT security with asymmetric, because people don't care how long it takes. But that wrecks a machine-to-machine communication, and I think that's the explanation you needed. Does that make sense? So other places, isolated network. So if the network's isolated, you just need a key to prove or to authenticate a message authentication code and verification, or if you need a key for a one-time encrypted communication, why the network's disconnected, creating symmetric empirical keys. And reprovisioning of vendor circuits or secrets, and rapid exchanges. So you don't want to asymmetrically, if you need to operate a breaker out on a circuit, you don't want to have an asymmetric cryptography to do it because it has that unknown time. So that's when these, your symmetric keys will be used. When would the asymmetric be used? Cross-industry support. Anytime you're communicating between industries, all these are going to have one feature: no time dependency. Provisioning credentials. So in the provisioning time, or setting up sessions. So if you're reading a device, the meter data management doesn't always have to have real-time information. It can have a little bit of delay. So that's when you can use, that's when symmetric comes in. Reprovisioning on compromise, a little bit of leeway in time. Privacy exchanges. Another one where asymmetric works, you wouldn't think about it, and I don't have it on here, is in the initial boot verification on the onboard system trust. Because when you're starting up a system, you're tolerant until it comes on the network to its operation time. So you can use an asymmetric algorithm there. But this just kind of goes to show why I say that you need both in here, because at different places, every device has to have these different timing requirements. I don't know how much I'll let you look at this, but this programming transport that I kind of talked about, that you set up, like we set up with an Asian vendor, and how that's worked to install vendor information, and doing so without anybody that has access to programming it knowing what those secrets are. So now we look at this next section is going to talk about things for these secrets management in the network systems between organizations, authentication, system, and secret rotation. But it supports that gap between synchronous and asynchronous. Now, if I wanted to say, whenever we're in what I'm calling kind of the governance, when you are programming that network. Now, the next base, the last one you saw, we programmed using the transport, the vendor. Now we're programming using the vendor, the network. So these features now, the last programming slide, I'll go back to it actually real quick. And this one are operations that are very valuable, not being done too much or being done just ad hoc by whoever brings it in, does the firmware, does the programming. But there's a whole industry here of this programming steps that will really have to develop. So at the governance, you have the multiple vendors. So now if you go back and look at this, I could take this network and make multiple of these. So if you're a PEP and you're going from one network to another, I just make a new block at the network level. And you add that capability into the central DNA to be able to have multiple networks for roaming loads. And kind of, in talking to the auto manufacturers, there's three kind of billing things they're looking for. Local kind of billing to your, you use pay billing, credit card stations or whatever, and billing to your home, and then somebody, human, go ahead.
This is for electric cars?
For any kind of roaming load.
Okay.
I'm saying electric cars is the biggest roaming load I can think of, but there's more. I'm sure. You know, a generator that they haul around from place to place, a carnival that moves around, anything you can think of that changes location. But the kind of consortium with autos is looking for, those three kind of use cases, and without going into details on it, you can support all three of those with this kind of security base in each device. And here's kind of how you do it. You just add another block. And the thing you can do is you can double sign the home one for the roving one. So now when you want to make a roving block, you take the home block, you communicate with their CA, verify that it's them, double sign it. Now they have non-repudiation of charges. Now, as far as how's this block used in the onboard system integrity, maintaining that chain of trust, and then protecting restricted access to the secrets, and then transferring over that to the network. And this drawing you'll see in a lot of my publications and everything. But in the configuration, you hash the configuration as part of the boot up process to verify that the configuration hasn't changed or that it is the device that the software is designed for. And then that verifies the operating code before it allows it to run. Then the operating system then verifies each application before it allows it to run. And then the application turns over and verifies itself to active trust management on your network. This is kind of how the chain of trust would use internal secrets on an onboard system startup. Let me know if you have any questions on this one. I think I have a couple. So it's extended from Providence to the onboard verification. The bootloader verifies the code before it's running, and the operating system verifies applications. This is kind of when you're looking at why you can't run a non-approved app on your iPhone. It's because the Apple OS is looking for that certificate from the application before it allows it to run. Before it allows it to install even, actually. So protecting those secrets, this is something that we did a lot of work with OpenSG on. And I put this slide up before, but that cryptographic key is the thing that's different in the memory. Even blank memory has patterns, and usually it's all white with a couple of random bits set here and there. But a really unique diversification of bit patterns is actually even encrypted data isn't as perfect. There's actually the OpenSG project. I'm not going to go into this one, but you can pull this up on the UCA site. But it's, what piece, and I said I'm not going to go into it, then I'm pointing at it. What pieces are required and how you transition from piece to piece across buses, protecting them was kind of the object of this routine. For protecting firmware, you can make a signature on the firmware that doesn't allow it to install unless it has a signature that comes down with it. Now that you have provable cryptography on board the device, the self-trust, you can enforce this. What kind of secure boot? Right here I'm not going to go into these, I'm showing an asymmetric method of secure boot and an symmetric, both possible. Network synchronization. Bridging at this level is where we're really starting to think a lot about bridging between ICS and IT security basis and what enables that to happen. And you think in terms of synchronous operations, you have to do a couple things. Be able to produce a unique key anywhere on the network for temporary use or whatever, and then be able to take that unique key from that node, encrypt something with it, and send it up for use somewhere else. This is what this shows. Use higher level in the network. And then any node be able to authenticate uniquely, so produce a message authentication code and then authenticate it on the net somewhere else. And this is important in disconnected networks. So being able to continue security posture and using security in a network that's not connected up to enterprise network. And then be able to produce shared keys, the same key anywhere in the network. So these kind of three functionalities is what's required for symmetric operations. And then it can be used by any application that needs the key to use it. And what you have value here is that you can reproduce and produce these very fast. Encryption on the fly. Rapid support for that embedded system requirements. So now, this is a, when I talk about rolling, this usually comes with other slides. I pulled the other slides out, so I'm not going to talk about it too much other than say the identified blocks here are designed for using a network leg, and you roll off the network leg number, you can have a different cryptographic keying at every level of the network using the same base root for each level and just kind of pass it down. Synchronizing, how that will be done, tokenizing, time-based type of things. Like I said, I think this is too detailed. And then asynchronous, what you need there, exchange public keys as needed for use with asymmetric operations, either up to the enterprise systems or between nodes or between different applications. And then reprovisioning. And this is very well done with existing certificate authorities and PKI environments. Redoing certificates. This enables the cross model between multiple, and this is why you need the symmetric for the rapid and the asymmetric for now. Every time you plug your PEV into a different network, it can call home through your cross-network trust models. So operational key management, what's needed, what's there? For critical infrastructure, you need to reduce global static keys, so be able to rotate through them, be able to change them out. I don't know any manufacturer that has a good method of this. We'll just kind of leave it at that. Cross-industry support. Where's the cross-industry support done? A list of things you can, whatever you can think about here. All these fit into kind of that, the need for asymmetric. There's the cross-industry support added. And then kind of back showing this. This is the last slide I have. We can talk about anything you want. I breezed through the last stuff, but it's because it gets so detailed. Sometimes I get bored with it.
Questions, thoughts, guys, anything?
Very interesting, because the city is very rarely that you see this topic discussed with the ICS community. It's not something that it's often comes up, but it certainly can add a level of security to the networks and to the ICS.
Mm-hmm. So there's one thing, I will show a slide that I have here at the end that is the kind of the reason for everything. Back to the beginning of my, okay. So now if you have provable trust on every device, you can stamp data from those devices with the DNA of that device and provably, undeniably, non-repudiation back to that device.
But then this is not based on a mathematical crypto algorithm, this is
Yes,
another.
it is.
Hashing.
You would use, there's several ways to produce a proof of origin, but the best way is it's a signature. So it's the reverse of a PKI where you're actually signing. But you sign in a piece of the configuration,
Okay.
certain hash of keys block. You know, there's ways you can be very timepiece. You can, all that can be stamped right into the data, proof of origin, time, operations, and it adds the relevance of everything that's done here up to the enterprise systems.